So having just talked about the mutual information, you may not be surprised to know that we can talk about conditional mutual informations as well, the same way we talked about entropies and conditional entropies. A conditional mutual information is simply the reduction in uncertainty or surprise about one variable x that we obtain from another variable y, given the value of another variable z. We can interpret this in a few different ways. Firstly, we can think about interpreting this as a mutual information that's simply taken in the context of z. And to look at that, all we do is change all the maths we already had for mutual information, change all the terms to be conditional on z. Okay, and that's exactly what we get right here. We take all the maths that we already had for the mutual information between x and y, make everything conditional on z. So there's all the same terms we saw before, just conditional on z now. And okay, I should admit this one down here isn't new. This is a different way of looking at it. We can look at a conditional mutual information between x and y given z as a mutual information between x and y and z taken jointly minus the information from z about x. But otherwise, everything's the same as it was, just conditioned on z now. The properties we can look at in the same way, simply taking the context of z. So the conditional mutual information here is now capped by the minimum conditional entropy of x or y given z, whereas before for the mutual information it was capped by the marginal entropies. So here we can see that if z explains x, for example, that is there's no uncertainty left in x after we've considered z, then we're going to have zero conditional mutual information because this zero term will be a cap on the conditional mutual information. Similarly, the conditional mutual information is symmetric in both x and y, the same as the ordinary mutual information was. Furthermore, we can see that the conditional mutual information is equal to the entropy of x given z. That means all of the remaining uncertainty in x was explained by y after we had considered z. And that's exactly what we see here. There's no uncertainty left in x after we've considered both y and z. To try and make a diagrammatic interpretation though using Venn diagrams of conditional mutual information terms is difficult, and I need to warn you about doing that. You can draw a Venn diagram with three different variables here, x, y and z. All of the areas in these diagrams will add up correctly as they should. So all four areas here will add up to give you the total entropy of x, for example, and we can identify a conditional mutual information between x and y given z. So taking our intuition from before and saying, well, z explains some of what's in the joint variable x and y, so we just sort of cut this part out and then look at what's left between x and y given z. That will work. That will be the piece you identify in the diagram. The warning comes in because the diagram gives the misleading impression that all the areas on the diagram are positive, and they aren't necessarily always positive. In particular, the very middle piece here is not necessarily positive. Okay? That's a really important thing to note, that this last little piece here is equal to the mutual information between x and y minus this conditional mutual information between x and y given z. And that difference there, that piece, is not necessarily positive. Okay, so this is why Mackay warns very explicitly that there are no other well-defined three-term entropies apart from conditional mutual information terms, and suggests that we shouldn't really use these Venn diagrams beyond two variables. Okay, so let's look at an interpretation that does hold. We can extend our interpretation of chaos divergence and the Bayesian view from mutual information straight to conditional mutual information. This is another easy one. We're just coming into our mathematics and making everything conditional on z here. We can think this term here, the joint probability has already kind of absorbed that conditional term and then averaged over the probability of z as well. Here we can see the first equation here is showing us that the conditional mutual information is just the KL divergence between the joint probability of x and y given z and the conditional marginals here as well. Okay, so what we see is the conditional mutual information is a code length penalty for coding x and y, assuming that they are conditionally independent on z. Okay, it's a code length penalty for coding under this scheme rather than the real scheme here, if everybody knows z. Or equally, we can think about it as a coding penalty for coding x without knowledge of y in addition to knowledge of z, versus if we had encoded it with knowledge of both variables. Moving on to a third interpretation, we can give a statistical view of the conditional mutual information as well, in the same way that we did for the ordinary mutual information. Here we have the property that the conditional mutual information is 0, meaning that x, conditional on z, is independent of y, or vice versa. We can also think about the conditional mutual information as a nonlinear form of partial correlation, the same way that mutual information was seen as a nonlinear form of ordinary correlation. We can also think about pointwise or local conditional mutual information terms here, the same way we thought about pointwise or local mutual information terms earlier. Here again we can write down all of our equations for the pointwise terms, simply conditioning them on z. Okay, so that's a fairly straightforward one. And again, the pointwise conditional mutual information terms may be positive or negative in the similar fashion to how the pointwise mutual information terms were positive or negative before. And of course, our average conditional mutual information must be equal to the ensemble average of the pointwise conditional mutual information terms.